Hello and welcome back. In the next few lectures, we are going to discuss what is called the method of generating functions in combinatorics. This is a very powerful method and it is especially useful when we are dealing with the following kind of situations. So, as we have noticed, we have several situations where we have a parameter like which is probably a natural number, and associated to this natural number, we have a number which comes as the number of objects of certain combinatorial structure. For example, you can talk about the number of permutations of an n-element set, right, which we know is n factorial. Or you can talk about the number of graphs on an element vertex set, or you can talk about binary words of a specific length, let's say n, right? Binary strings of length n, or let's say lattice paths, of n steps, or let's say triangulations of a polygon, or we can talk about the number of polygon with n sides, and we can talk about the number of ways of bracketing a product of n matrices. Right? So all these examples, we have a natural number n, and associated to this number, we have the number of objects of a particular type. So now this particular situation gives rise to defining what we can call sequences or counting sequences. Now, generating function gives a nice way to encode the entire sequence into a function form, right? It's a nice form, which can be immediately decoded, or decoded to get a specific value, for a fixed parameter that we want, right, or a parameter that we want. So let us first look at what are counting sequences, right? So what is a sequence? So a sequence is nothing but a function from the set of natural numbers to let's say real numbers, or natural numbers itself. It could be anything like that. So basically, a sequence is something which we can put it into order according to the natural numbers. Say for every natural number including 0, let's say 0, 1, 2, etc., we can associate this number, and then that defines a sequence. For example, here is a sequence, 1, 2, 4, 8, etc. So how this sequence came about is that, like, I'm looking at the number of binary words of length n. Okay, so let's say that W is the set of such binary, all of binary words. Then I can arrange W, right, as follows. Like, we put the number of strings with 0 letters, which is the empty string. Then we have 0 and 1, which are the one-letter strings. Then you have 0, 0, 1, 0, 1, 1, and 0, 1, which are the two-letter strings, right? This way we put this set. And then we can talk about Wn, which is the set of binary words of length n, right? So Wn, whatever, how many numbers are there, we know it is actually 2 raised to n, right? We 2 raised to n strings using 0 and 1. And therefore, we have the sequence Wn, which is sequence 2 raised to n. So basically, it's a function from the natural numbers 0, 1, 2, 3, etc., to 0 going to 1, right? 1 going to 2, 2 going to 4, 3 going to 8, etc., right? So basically, n going to 2 raised to n. So this is basically a counting sequence because it counts the number of binary words of that length. Right? So that is one nice example of a counting sequence. Now we can look at other examples. As we said, like we can look at the number of permutations. We know it's n factorial for an n-element set. So therefore, I can talk about the sequence Pn, which is basically 0 factorial, 1 factorial, 2 factorial, etc. Right? And that is the counting sequence for the permutations. Similarly, we have Tn. The sequence Tn counts the triangulations of a polygon with n sides, and we know that it is basically the Catalan number, right? We discussed this before, and therefore we have the sequence Tn to be sequence Cn, where Cn is 1 by n plus 1 times 2n choose n. So these are examples of counting sequences. Now, once you have a counting sequence, our idea is to put it into a nice function form, right? And then try to use this function to do several manipulations. And whenever we want, we can retrieve this information immediately. That is the idea. So to do this, what we are going to do is to define, what is called formal power series. So before going to formal power series, let us see what is a power series. So given any sequence, right, sequence of real numbers, let's say sequence an for n greater than or equal to 0, we can associate a power series by multiplying an with x raised to n and summing over all n. Right? So this does two things, right? One is that like you can now write it as a sum, and when you do this sum, we can still recover an as the coefficient of x raised to n, right? Because when you have powers of x, right, which is a variable or indeterminate, we cannot add them together, right? So we can just write it as a sum, but if I have x and x square, I cannot add them, right? X plus x square I can write, but I cannot add it. So this helps to get back an, right, by just looking at what is the coefficient of x raised to n. Now, in some cases, like in power series, we know that if the power series converges, it usually converges to a function, and if you have a nice function, then we can use that function as a placeholder for the power series, right? And then whenever we want, we can retrieve back the coefficients by using the Taylor series expansion of the function and evaluating at x equal to 0, right? And then you can find out this series and its coefficients. So this is something it's standard, can be done. Now, so in the following example of a power series, summation x raised to n, where you have the constant sequence 1, 1, 1, etc. Right? So an is 1, 1, 1, 1, etc. Right? When an is 1, so sequence an is sequence 1, 1, 1, 1, etc. Then maybe I should write this way to know that this is a sequence, right? It's not a set. Okay, so now, so if all the all the constants are 1, then we have summation x raised to n, and we know that this series converges to 1 over 1 minus x whenever mod x is less than 1, right? So how do you do this? How do you prove this? And this is something that we have studied in calculus. So suppose I have summation x raised to n. So I have, so let us say that t is equal to 1 plus x square plus etc. Then I know that xt is equal to, right, x plus x square plus etc. Right? But this is the previous sequence minus 1. The first term is missing. So this is equal to right? So from this, it's t minus 1, right? So, tx is equal to t minus 1. So from this, we can find out what is t. So t is equal to 1 by 1 minus x, right? So this we can find easily. So we solve for this and we get the function, nice function. And if you take the Taylor series expansion, you can recover the series. Okay. Now, we are going to work with what is called formal power series. So, when we say formal, it is formal in the sense that, when we add or some operations with this series, we have to keep in mind that we are not really adding, we are only, writing it as a formal sum. And it also, emphasizes the fact that the series that we look at may not always converge. Okay, and we don't really worry about the convergence, because what we want is a way to put all the the information about the sequence in a nice form, and we are not going to evaluate it at at a point for x, just to so therefore the convergence really doesn't matter to us, right? So and we know that when x equal to 0, it's going to converge, but it doesn't converge in an interval. Still, we can use this series. But when we work with power series, and if it doesn't converge, people might object that, okay, this is not really right. We cannot add these two things because they are both diverging. But then we say that, okay, it doesn't matter because we are not really looking at the sum, right? We are only looking at the coefficients, and whenever we are going to look at, we are only going to look at finite coefficients, and therefore we are only worried about that, and it doesn't matter whether the entire series converges. So therefore we define what is called formal power series, where we don't really worry about the convergence issues. So the analytic properties need not always hold, but whenever it holds, we can use it to get some nice forms. So we will write it as formal power series most of the time, but when we can really use the analytic properties, sometimes we can use the convergence, but that we don't discuss it in this course. Only when we look at more advanced topics, we might need to look at evaluation of the generative functions or power series at some point. Okay, so without further ado, let us see what is a formal power series. So formal power series is an expression of the form summation an x raised to n, where sequence an is a sequence of coefficients of elements from typically a field. Okay, so we are going to look at with the assumption that we are going to draw the coefficients from a field, and let's say field k, and most of the time we will assume these coefficients that the field of coefficients contains the set of the field of rational numbers, right? For example, we look at q, r, or c, right? The rational field, the real field, or the complex field. But it is not necessary that we can we not always it doesn't, it's not important that it is a field. We can also work with the cases when k is a ring also. Now we will not discuss these things for the time being. We will just assume this to be the case. So we have the formal power series which is defined over this field k, and it basically takes the sequence an and then multiplies the term ai with x raised to y, and then sums over all I, right? Now Let us look at some examples. So here is the first example, f of x, which is 1 plus 2x plus 4x square plus 8x cube plus etc. Right. So this is basically coming from the let's say the sequence of binary words, right? The number of binary words of length n, and that will tell you that the function is 1 plus 2x plus 4x square plus etc. because the n element length n string has exactly 2 raised to 2 raised to n possibilities. Okay. Similarly, we have another sequence. Let us say sequence n, right, where 1, 2, 3, etc. is the sequence. So what is the power series, which is summation n x raised to n. Then you have summation n factorial x raised to n, which is another series, which is the series which represents the number of, let's say, permutations of n elements. Then so these are all examples of power series and formal power series. And in this particular case, when we have the constant sequence 1, right, we have summation x raised to n. That sequence, for example, can be written as 1 by 1 minus x, as we showed before, because it converges for values of x where mod x is less than 1. So and in that interval, because it converges to 1 by 1 minus x, we can always write it as 1 by 1 minus x. So if the series converges for any interval, right, any small interval, no matter how small, we can write it as that function, right? So we can use this to help putting the entire information in the series directly to this function, and that is what we are going to use in our calculations often. So we saw that f of x is equal to 1 plus 2x plus 4x square plus etc. Right? Now, since we know that 1 plus x square plus etc., right, which is the summation x raised to n, is 1 by 1 minus x, let us replace x by 2x, right? So x is an indeterminate, so therefore 2x is also an indeterminate. So if I replace x with 2x, then I will get the series 1 plus 2x plus 4x square plus etc. But since this converges to 1 by 1 minus x, I can say that this say series 1 plus 2x plus 4x square etc. converges to 1 by 1 minus 2x, right? So because I just replace x with 2x, I get this. Now, of course, the convergence of this is in a smaller interval, right? So now instead of converging for mod x less than 1, it converges for 2 times mod x less than 1. Right? So this way we can use the so for any constant, now we can say 3 raised to n x raised to n can be, right? The sequence 3 raised to 3 raised to n x raised to n or k raised to n x raised to n, we can put it into 1 by 1 minus kx kind of form. Now, a slight deviation from our formal power series. This is because we will need this generalization of this binomial coefficients to use sometimes in calculation, right? So this will help. So we already saw that the binomial coefficient, right? So given two natural numbers, let's say n and k, where n is greater than or equal to k, we have the binomial coefficient n choose k, right? Which we came across because it is the number of ways to choose a k element set from an n element set. Now, so we found out that this n choose k is actually n into n minus 1 into n minus 2, etc. N minus k plus 1, right? The first k times divided by k factorial, right? This is something that we proved earlier. And then we said that, okay, we can also write it as We can also write it as n factorial by k factorial into n minus k factorial. And this was possible because n factorial is basically 1, 2, 3, etc. up to n. And what we were looking at is n into n minus 1 etc. n minus k plus 1, right? So therefore, if I take n factorial, it has all these terms. But then to remove the last n minus k terms, I have n minus k minus 1 etc. up to 1. And that goes to n minus k factorial, right? So therefore, I could have done is to replace this by n factorial by n minus k factorial, and therefore I got this nice expression. On the other hand, when we look at generalized binomial coefficient, we use the previous case where we the definition, where what we have is n factor instead of n factorial we have n into n minus 1 etc. by k factorial. So take this definition, right, and then let us define for a real number now, right? So a is a real number and k is a natural number. So for this case, we are going to define a choose k as the generalized binomial coefficient. So what is a choose k? It is a into a minus 1, a minus 2, etc., a minus k plus 1 divided by k factorial. Now, one can ask like, why does this make sense, right? So we will see this, when we see some applications. But of course, this is perfectly, well defined because we have all these things. Even though we cannot define, for example, a factorial, we can define this easily. So we have the generalized binomial coefficient a choose k in this way. Now, as an example, let us look at this 1 by 2 choose 3. Right? So what is 1 by 2 choose 3? It is 1 by 2 into minus 1 by 2 minus 1, which is minus 1 by 2, into 1 by 2 minus 2, which is minus 3 over 2, and divided by 3 factorial, which is basically 6 into 8, 48, 3 by 48, which is 1 over 16. Right? So we have this. We have this expression and the binomial coefficient for 1 over 2 choose 3. So this could be useful, as we will see later. Now, we can also now define the generalized binomial theorem, right? So binomial expansion is 1 plus x whole raised to a, right? So instead of 1 plus x whole raised to n, we have 1 plus x whole raised to a for a real number now, which I can write as summation a choose n x raised to n for any real number a, and n being natural numbers, right? N greater than 0. Now, how do you prove this theorem? Well, what you do is that we look at the Taylor series expansion of the function 1 plus x whole raised to a. So what is the Taylor series expansion? We take the nth derivative, right? So 1 plus x whole raised to a, take the nth derivative. What do we get? We will get a into a minus 1 into etc., right? We will get, if you take the nth derivative 1 plus x whole raised to a, we will get a into a minus 1 into etc., a minus n plus 1 into 1 plus x whole raised to a minus n, because we have taken the derivative n times. Now, we want to evaluate this at x equal to 0, right? So then what we will get is a into a minus 1 into a minus 2 etc., a minus n plus 1. And what Taylor theorem says is that this is precisely the coefficient of x raised to n by n factorial when we try to expand, right? So because it is the coefficient of x raised to n by n factorial, what is the coefficient of x raised to n? That is going to be this divided by n factorial, right? Now, what is this? A minus 1, etc. A minus, when I say this, it is only the time up to here, because when I substitute for x equal to 0, this time becomes 0, right? So this becomes 1, right? So this for, so therefore, I just have this, which is the definition of the binomial coefficient a choose n. So therefore, since I know that the coefficient of x raised to n is going to be now a choose n, right? And therefore I have the theorem. So that is the proof. Now, we once we have this, we can use this to, for example, expand a given function. For example, 1 by 1 minus x, I can write as 1 minus x whole raised to minus 1. Now, minus 1 is a real number, right? And I have 1 plus minus x whole raised to minus 1. Therefore, I can use the generalized binomial expansion, which will tell me that it is summation minus 1 choose n minus x whole raised to n. Now, what is minus 1 choose n? It is minus 1 into minus 2 into etc. Minus n divided by n factorial. But this is minus 1 whole raised to n divided by minus 1 whole raised to n into n factorial divided by n factorial. So n factorial cancels out. I will get minus 1 whole raised to n. So now this is the minus 1 choose n time. So then I have minus 1 whole raised to n and minus x whole raised to n. So these together will give me x raised to n, right? So therefore I get summation x raised to n. So this is another way to expand using the binomial theorem, generalized form. Now we can define the whole algebra of formal power series, right? So we can define addition, we can define scalar multiplication, we can define product, all these things, and then one can show that it actually forms a ring. Okay, so we can call it the formal power series ring. Now we will not go into the details of this because that is not part of our course. But we will just state a few things, and we say how do the addition and multiplication work. Okay. So given two series, let's say f of x is equal to summation fn x raised to n, which is the first series. Then you have another series g of x, which is summation gn x raised to n. Now, given these two, I can define the sum of the series f of x and g of x, which is f plus g of x. So f plus g is the sum. So f plus g of x is basically summation fn plus gn x raised to n. This is clear because now when we have two formal power series, right? When we take the sum, we can only add, for example, the coefficient of the like terms, right? The corresponding terms, x raised to n. I have to take the coefficient and then add with the coefficient of x raised to n. That is the only way we can add. Therefore, it's a natural way to define the sum, right? Now, what will be interesting is when we see how this can use these kind of operations to define what happens in the combinatorial structures.